In this video, we're going to continue making plots in Matlab. We're going to make two kinds of plot. One will be a histogram, or the amount of area per unit elevation for the whole Earth. And we're also going to make some maps of elevation or depth of the ocean bathymetry, and maps also of the precipitation rate. And the motivation for looking at elevation and precipitation is from this book by David Mackay on sustainable energy without the hot air. And if you go to chapter 8 on hydroelectricity, they have this plot in the bottom which shows a histogram of the amount of area per unit, or as a function of elevation. So every box here, these are rectangles, are proportional, their size is proportional to the area in each elevation class for the United Kingdom. So we're going to try to do an analogous figure, but for the whole world, using the ETOPO1 data set. And the reason we care about elevation is if you want to make hydropower, you need to have rainfall at height, so you need mass of water, and you need height. And so the precipitation rate data set is going to be used, or can be used, along with the elevation to find out how much potential energy you could in principle get. What is the upper bound? And so we're going to make these plots. So the book by Mackay is, I think it's available online for free, so you can get it there, but it's quite good. So if you are interested in how we think quantitatively about sustainable energy, this is a good book. All right, so the data we're going to use is available from the NOAA website. The ETOPO1 global relief model has a 1 arc-minute resolution elevation, positive for continents, negative for the ocean basins. So 1 arc-minute, that's 1/60th of a degree, both in longitude and in latitude. And the data is available in NetCDF, and so that's the file that I downloaded. And then on the same site, they have this picture over here called the ipsographic curve. And so the upper panel here, this one here, the right hand side, and the upper part of the right hand side has this histogram of area as a function of elevation. So it corresponds, this part corresponds to this graph in Mackay's book. So there's a little bit of a problem though. In Mackay, they label the rectangles in area, so the number of square kilometers in each height bin, which is correct. On this graph on the NOAA website, they label the axis here, the x-axis, as area in square kilometers, but in fact it's not correct. It's not the area, it's the area per unit elevation. So you only get the area if you multiply the height by the horizontal, not the horizontal, the vertical length in this direction, right? So it's the area of the rectangle which corresponds to area on the surface of the Earth. Same thing here, it's the area under the curve that corresponds to the area on the surface of the Earth. So the height doesn't have units of area, it's a density per unit elevation. So it's area per unit elevation. All right, I hope that's clear. I'm going to correct that when I make the plot myself. And on the right hand panel of this figure, they have the cumulative distribution where they've summed up the full density, and so you can get the total amount of area that is above, that has elevations above a certain level. So for example, over here, right, this is the part that's above sea level, and where it crosses to become negative, it's down here, is close to 30. So because around 30% of the surface of the Earth is covered by land, and around 70% is covered by oceans. The figure we're going to make. So let me show you these figures. I've done them already and saved them. This is this same plot, but now the x-axis over here is labeled correctly as area per unit elevation, or in units of kilometers squared per meter, not kilometers squared as in this figure. And the right hand panel is correct. It's the fraction of the surface area. So 100%, so the whole surface, the elevation is more than negative 11,000 meters. the deepest point in the ocean is not quite 11,000 meters deep. All right, so this is the right-hand side is the integral of the left-hand side. And if you want to see the map, this is the map of the eTopo bathymetry dataset. The resolution here is only every 5th pixel. So the 160 at 1 arc minute is too high resolution to put the contours. It took forever to plot it. In fact, if you try to do the contours, I think my computer was crashing. It was running out of memory. But it shows the color bar, shows the elevation. The black contour is the separation between the continents and the ocean. And the oceans are in blue-green and the continents are in brown. And you'll notice that the plots have the correct geographic labels in degrees west instead of -180 to +180. All right, so let's look at how these plots are constructed. Here's the Matlab script over here. And so this is the file name. I put the URL where I got the data in the file so that when I come back at it sometime in the future, I'll be able to go back and find where I got this data set. The variables in the file are x, y, z, where x is longitude, y is latitude, and z is the elevation. So if I run it, example 4, you can get the size of z. So size of z, it's very big. So there's 10,801 pixels in the y direction and 21,601 pixels in the x direction. Right, so this is the bathymetry image. So this one shows up pretty fast, and the reason it's fast to plot is I converted the data to an 8-bit integer, unsigned 8-bit integer, using this ubint 8. And then Matlab has a function called image show. So normally the data in the variables in Matlab are going to be double precision, but for these images, this is very slow to plot. And so if I rescale z, the height, by subtracting the minimum, so the smallest value of z, of I guess, will be 0, and the biggest number will be 256. So I subtracted the minimum, and then I divided by the range from the maximum to the minimum to rescale the whole thing between 0 and 256, convert it to an integer, and then I plot it. So this one is fast to plot, and we can zoom in, for example, over California, and you can see all these details, these beautiful fractal patterns, and over here is the ocean. So you see all this beautiful fractal geometry. It's quite impressive, with very high resolution. And you can change the color map to make it easier to see if you want. So the color scheme that I have here is just the default grayscale, but you can pick different colors and you'll get prettier figures. All right, so that was just to show you the data. After that, I make the plot of the map. And as you can see over here, IX and IY is every 5th index. So I skip 4, I guess. And I do that so that it's quicker to plot using the pcolor command. And I choose the color levels on my color bar. So from -11,000 to 11,000, those are going to be the tick marks. I label only every other tick mark, so I skip one so they're not too crowded. I set the label for the color bar to be in meters. I generate the color map. So I use this function called Brewer map, and you can get this. It's not available from the Matlab distribution. You have to download it separately. So if you go to the MathWork website, you can download a function called Brewer map, and it will construct these pretty color schemes for your color bar, for your color maps. And I picked the brown, blue-green, this one here, to generate the map. So blue-green for the ocean, brown for the land. Since it's increasing from brown to blue-green, if I just use it as it's constructed, I would have the oceans be brown and the land be blue-green. So what I did is you did this flip up-down, so I reversed the orders of the colors to go from green or blue-green to brown, so that the continents will be brown. And then do the color map, set the tick bars, and so on, and make the plot. I also plotted the contour, the black contour, that's done on here. Contour, and the 0 contour, that's the one that separates the continents from the ocean. And after that, we want to do the histogram and the hypsographic curve. So for this, I need to know, it's not just enough to do a histogram where I count the number of pixels in every elevation bin, because some pixels, not all the pixels have the same area. So if I move around the longitudes, of course, they all have the same, they don't change, they're all the same area. But as I move more south, north or south, the width of the bins gets narrower because they're a constant width in terms of angle, but the meridians are converging towards the pole. And so you get a smaller area the closer to the pole you are. And so you have to take that into account. So if I go back to my document camera here, let me show you. So if this is the Earth, it's supposed to be kind of round, and this would be the equator. And here I have an equatorial radius, and then the vertical axis. This direction here, let's change color. This direction here, this is the longitude, which I'm going to call lambda in radians. So lambda is the longitude in radians as opposed to in degrees. So to go from degrees to radian, oops, you multiply by pi divided by 180 degrees. All right, because a full circle is 2 pi, the circumference of a circle is 2 pi, and there's 360 degrees. So that's lambda, and then phi goes in this direction. So in this direction, this way, I have phi, which is the latitude in radians. So if I pick two lines of constant longitude, you can see that the spacing between them is going to be a function of what your latitude is. So it's going to be a function of this angle over here. If you're close to the equator, you're going to be farther apart, and if you're close to the pole, you'll be closer together. So the typical area element looks something like this, where this here is d lambda, and this angle is d phi. And so in terms of distance, the distance for d phi, so this distance here, delta x, or delta y, sorry, and this one delta x, is the following. Delta y is equal to the radius a times d phi, and the delta x is a cosine of latitude d lambda. So phi is equal to 0 at the equator, and is pi by 2 at the North Pole, and minus pi by 2 at the South Pole. And as you approach the pole, cos of phi goes to 0, and so the spacing goes to 0 as you approach the pole. And so the area element, delta A, which is equal to delta y times delta x, is equal to a squared cosine of phi d lambda. And so it's this cosine phi here that means that not all the pixels have the same area. They vary according to cos phi. Oh, a, by the way, is the radius of the Earth. I'll put that up here. So what I've given you here is the case for if the Earth was a perfect sphere. In fact, the Earth is what's called an oblate spheroid. So it's, I'm going to exaggerate here, but it's kind of fat around the equator and flattened towards the pole. And so the equatorial radius over here, this one, B, is bigger than the polar radius because the centrifugal force causes the Earth to bulge out around the equator because it's spinning around. And so from this we can define what's called the eccentricity. E squared is equal to 1 minus c over b squared. So if C and B were equal to each other, the eccentricity would be 0, so it would be a perfect sphere. But because B is bigger than C, this E squared here will be a little bit less than 1. And that E squared is going to appear in a correct, better formula for the area element. So they have that on the eTopo model website. So if I go back to the browser and I go to the ipsographic curve down here, they give the functional form of the area element that includes this eccentricity here, E. And I think in this case A, what they call A, is the equatorial radius, what I labeled as B over here. Okay, so that's so now what I need to do is not just count the number of pixels that fall into every elevation, but what I need to do is add up the areas of all the pixels that fall into every elevation bin. And so that's what the code does after that. So if to do the histograms, I use Matlab's hist_c command. Let's see. First of all, let me back up a little bit. First thing I do is I convert the y and the x into phi and lambda, into radians. Then I make a 2D mesh of lambdas and phis, and I compute the area element using the formula on the NOAA website, including the eccentricity. And I have the cosine of latitude, so I get all the area. So every pixel has an area. So the dA, if I go back to the figure, the Matlab prompt, dB continue, dA is going to be an array of the same size as Z, so 20 some thousand by 10 some thousand. And then I'm going to bin all the heights, the elevations, into different elevation classes. So I've divided up the whole range of potential elevations from minus 11,000 to plus 9,000 in steps of 5 meters, delta H. And so the hist_c command will assign each pixel an index, I, which will reference it to which depth bin it falls within this H category. And then what I go back and do is I sum up all the dAs that have a common index I to get C, which will be the amount of area in each elevation class. And some of the bins don't happen to not have any elevations, and so for those I just add 0 to those. So out, in the end, the variable out is what I'm going to plot along this axis over here. And I'm going to plot minus out so that it points towards the left as opposed to towards the right. So you'll see down here, where is out? Yeah, plot out, minus out. Right, so that's so that it goes in this direction towards the left. You'll notice also that when I do the accumulation, I don't just sum the area, I sum the area and I convert it from square meter to square kilometers by dividing by 1,000,000, right? So one square kilometer. So if this is 1 kilometer by 1 kilometer, that's the same thing as 100 meters by, 1,000 meters by 1,000 meters. So the number of square meters is 10 to the 6 is equal to 1,000 squared meters squared. So to go from squared meters to squared kilometers, I divide by 1,000,000. And also I need to divide by delta H. Right? So what I'm plotting here is the density, the amount of area per unit elevation. So I need to divide by the delta H. If I had picked this to be 10 instead of 5, then if I don't divide by delta H, then the height of the curve will change, because then it will be incorrect, right? It won't have the right units. So this is C, or out, both of those have units of area per unit elevation, or kilometers squared per meter. H is in meters, so this is a 5-meter interval. All right, and then after that I do the plot. To do the the cumulative, the hypsographic curve, the cumulative density, then for that one I just sum using Matlab's sum. So I integrate. So cumulative sum is going to sum up all the areas. So to get back the area from out is a density. It has units of area per unit elevation. If I multiply by delta H, then it's an area. So the cumulative sum will have all the sums of all the areas. I then divide by the total area of the Earth. So if I do sum of out star dH, I get the same answer as if I sum dA. Oops, sum dA divided by 1,000,000. 1E6. So this number and this one, they're the same. They correspond to the total area of the Earth. So 5.1 times 10 to the 8 square kilometers is the surface area of the globe. And over here, I'll just have the cumulative sum divided by this. So this will be a number. This quantity here will be a number between 0 and 1. And then I subtract that from 1 to get the hypsographic curve, so that it starts at 0 and goes all the way up to 100% once I've summed up the whole area. After that, it's just a matter of doing the labels and saving the figure. Okay, so that's how we do the bathymetry plots. The next one I want to show you is the precipitation data set. So very quickly here, if I go back to the NO website, there is this product called the GPCP data set, and GPCP is for the Global Precipitation Climatology Project. And on that site they have the precip.monthlymean.nc. So in this file there are 42 years of monthly mean precipitations in units of millimeters per day. So what I do, let me bring up the file, example3.m, is after I read in the data, I'm going to sum the rate of precipitation multiplied by the length of time for each month. So not all the months have the same length. So January, for example, has 31 days. February has 28, provided it's not a leap year. March 31, and so on. So in the data set, let me show you this. Close all, clear all. And let me run example 3. So there's a keyboard here, so you can see what's going on. And inside the file there's going to be a variable called tbounds. And it tells me the day, the time for the beginning and the end of each record. So for 2 for the second one, for the third one. And if I take the difference between these two numbers, I get the number of days for that particular monthly mean. So delta t here is the number of days in each record. So 31, this would be January, February, March, April, May, June, and so on. All the way up to the last one, which has 30 days, paradoxically, because that's a December. So the total number of days, the total number of months is 504. So size of P, it's got 72 latitudes, 144 longitude. The resolution is 2.5 degrees. It has 504 monthly means. So 504 divided by 12 is 42 years. So there's 42 years of data. The first month was January. The last one is December. For some reason there's a day missing in December. 31 in October, 30 in November, and so on. But for some reason there's a day missing in the last. If I count backwards, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is another December. So the other Decembers have 31 days. The last one is missing a day for some reason. In any event, the precipitation is in millimeters per day. You can check that. If I do the info for that netcdf file, h.variables name, It tells me all the names of all the variables, and I think the sixth one, let's see, let me count 1, 2, 3, 4, 5. The sixth one is the precipitation. So if I do 6, I get precip, and if I do the attributes, you get the name, let me get the name, and I think one is going to be the units. So number 3 is the units. So if I do the third, there's the units, and the units are, the value is in millimeters per day. So after I've sum up the total precipitation, TP, by multiplying the rate by the number of days in each month, I get the total number of millimeters of rain for the whole record, and the length of the record is T. I just summed up all the delta T's. If I divide TP by T, I get the mean precipitation rate, and in units of millimeters per day. If I divide it by 10, I get in units of centimeters per day, and if I multiply by 365 by 0.25, I get back millimeters per year. Or sorry, centimeters per year. The 10 converts to millimeters to centimeters. So I have the precipitation in centimeters per year in the end. All right, another thing I want to show you is that the values of x, or the longitude, right, they start at 1.25, so it's 2.5 degree resolution, all the way up to almost 360. But for the figure, I want to go from minus 180 to plus 180. So I have to reorganize the longitudes and the latitudes to get this plot. So the way I do that is I have a little function here that I created. I add 180 to the longitudes, and then I take the modulo 360, so to recenter it, and then I subtract back the 180 that I added. So that now the new longitude goes from minus 180 to 180 instead of from 0 to 360. But that means I now have to reorganize the precipitation, the columns. So the columns, the way I do that is I resort the longitude so that they're in the increasing order from minus 180 to 180. And then the I index tells me the new ordering, which I then use to permute the columns of P bar so that they're also in the right order. Otherwise, the from 0 to 180 is going to be the same, but then from 180 to 360 really corresponds to the first half of this plot over here. So from here, this is really 180 east all the way up to 360. Right, so that's from 180 to 360, whereas this is from 0 to 180. So I needed to reorganize, move this chunk of area from out here to the beginning. And I did that by first sorting the longitudes and reorganizing. Another thing I did is I added an extra longitude at the beginning and at the end. So you notice how it doesn't go all the way up to 360. There's missing a 1.25 degrees at the end and also at the beginning. And so that leaves an annoying little white spot of half a grid box at the beginning and at the end and the beginning, beginning and end of the file. So I avoid this by adding an extra longitude. Right, I took the first longitude and I subtract delta longitude, and I take the last one and I add delta longitude, and then I add the precipitation field at the beginning and at the end. So for the first one, I added the last value, and at the end I added the first value because it's periodic. So this line here is the same as this line, right? Because it's periodic in the longitudes. And so what I did is I copied the last one at the beginning. So I picked the last longitude and put it at the beginning, and the first one I put at the end. And now when I make the plot, there is no white gap at the beginning and at the end. After that, it's just a matter of making the plots. I also read the eTopo data to plot the black contour. Where's that? Down here, contour. I read the eTopo data and I plot just the zero contour to get the outline of the continent so you can know where the precipitation is. I use this Brewer map again. to set the color. This time I picked a green-blue color scheme, and I made sure that the number of colors in my map corresponds to the number of contour levels I want. So I plotted the precipitation in bins of 50 centimeters per year from 0 to 550, and then I put tick marks every 50 centimeters per year. And I made sure that the colors were discrete, so that and that they align perfectly with the tick marks. So that, for example, if I pick this band of light green here, I know that in this range the precipitation is somewhere between 50 and 100. And in this very light green area, almost white, then the precipitation between 0 and 50. And so on. So right, this darker green falls here. So I can know exactly what the range of precipitation rates is in all the contours. If you don't set the number of color levels to correspond to the color axis and your sea levels, then your tick marks can end up being in the middle of the color range, and it's hard to know what the value are of the colors. I think that's all the tricks there are to this. So I will upload the the script to the course website so you can have a look. Let's run the rest of the script. db continue. And here's this figure before it's plotted. So one thing that's a bit annoying, that's confusing, is that on the screen the font remains small, but when you print it to a file, you get a decently sized font for the tick marks. So sometimes you might want to make them bigger on your screen so that you can see them, and then when you print it out to a PDF like I do over here, they're going to be really, really big and look a little bit funny. So if you want to save a figure for a publication, then you have to be aware that the fonts may look different in the printed version. So you have to have a look. Okay, so that's the end of this video on making contour plots on a map and plotting densities or histograms. In the homework, you'll have a chance to play with these data sets to try to compute the total potential energy due to the precipitation, as depending on where the precipitation falls and what the elevation of the land is. You can compute the potential energy of that water if you were to dam it up and run it through turbines from the height at which it falls all the way down to sea level. So that'll be a fun exercise for you guys to play with the data sets.